Stars are so commonplace in the universe that it is easy to treat them as a kind of cosmic wallpaper, a default background of pinpoints that merely decorates the night sky. Yet the objects we casually call stars span a range of physical properties so vast that the word itself can be misleading. A star can be a compact sphere smaller than a mid-sized city, rotating hundreds of times per second, or it can be a diffuse, bloated envelope of gas whose outer boundary, if placed where the Sun sits, would swallow the orbit of Saturn. A star can pour out in a single second more energy than the Sun will radiate over its entire 10 billion-year life, or it can glow so feebly that even from a distance of a few light-years it would be invisible to the unaided eye. A star can contain enough mass to outweigh 100 suns, or it can teeter at the lower edge of hydrogen fusion, barely qualifying for the label. To understand why nature permits such extremes, and why some of them were not merely unexpected, but seemed impossible under the physics known at the time of their discovery, requires tracing several intertwined threads. The physics of nuclear reactions under different conditions of pressure and temperature, the behavior of matter at densities that have no terrestrial analogue, the role of magnetic fields whose strength exceeds anything achievable in a laboratory by many orders of magnitude, and the observational technologies that have allowed each new generation of astronomers to push the census of stars into previously inaccessible regimes. The most intuitive place to begin is with size, because size is the stellar property most readily grasped by everyday analogy, and because the extremes of stellar size reveal the most about how a star's internal structure can change over the course of its life. The Sun has a radius of roughly 700,000 kilometers, a figure that already dwarfs any human scale, but that turns out to sit comfortably in the middle of the stellar range. At the upper end, astronomers have identified a class of objects known as red supergiants, and among them a handful of stars whose radii approach or exceed 1,000 times the radius of the Sun. The star Ui Scuti, located in the constellation Scutum at a distance of roughly 5,500 light-years, was for some time cited as the largest known star, with estimated radii in the range of 1,700 solar radii, though subsequent measurements using more refined interferometric techniques and updated distance estimates from the Gaia Space Observatory have revised that figure downward somewhat, placing it closer to 1,300 solar radii, which is still an almost incomprehensibly large number. To convey what that means in concrete terms, if Ui Scuti were placed at the center of the solar system, its photosphere would extend well beyond the orbit of Jupiter, and possibly beyond the orbit of Saturn, depending on which estimate of its radius is adopted. The difficulty in pinning down the radius of such a star is itself instructive. Red supergiants do not have sharp, well-defined surfaces. Their outer layers are so tenuous, so loosely bound by gravity, that they merge gradually into the surrounding interstellar medium, and large convective cells on their surfaces, each one potentially as large as the orbit of Mars, cause the apparent diameter to fluctuate on timescales of months to years. Observations with the Very Large Telescope Interferometer have actually resolved some of these convective features on the surfaces of nearby red supergiants, such as Betelgeuse, revealing a seething, irregular photosphere that challenges the very notion of a single, well-defined radius. The star Stephenson 218, also known as ST218, is another candidate for the title of largest known star, with some estimates placing its radius around 2,100 solar radii, though these measurements are particularly uncertain because the star sits within a heavily obscured cluster near the galactic plane, making distance determination difficult and reddening corrections large. The pattern that emerges from studying these extreme objects is that the largest stars are invariably evolved, meaning they have exhausted the hydrogen fuel in their cores and moved on to burning helium and heavier elements in successive shells. This structural change causes the outer envelope to expand dramatically while the core contracts, and the resulting configuration is inherently unstable, prone to vigorous convection, episodic mass loss, and significant variability in luminosity and apparent size. These are not stars in a steady state, they are stars approaching the end of their lives, and the extreme sizes they achieve are transient, lasting perhaps a few 100,000 years before the star either collapses to form a neutron star or a black hole, or sheds so much mass that it shrinks back toward a more compact configuration. At the opposite extreme, the smallest objects that still qualify as true stars, meaning objects that sustain hydrogen fusion in their cores through the proton-proton chain, are the red dwarfs at the very bottom of the main sequence. The boundary between a star and a brown dwarf, which is an object too low in mass to sustain stable hydrogen fusion, falls at roughly 75 to 80 Jupiter masses, corresponding to about 0.075 to 0.08 solar masses. Stars near this boundary have radii comparable to that of Jupiter, roughly 1/10 the radius of the Sun, and surface temperatures so low, around 2000 to 2500 Kelvin, that they are extremely faint, emitting most of their energy in the infrared rather than in visible light. The star 2 mass, J0553 Serpinao 3, identified in the 2-micron all-sky survey, has been measured with a radius of roughly 0.086 solar radii, making it one of the smallest known hydrogen-fusing stars, and its luminosity is less than 1/10,000th that of the Sun. These stars are fully convective, meaning that material circulates from the core all the way to the surface and back, which is a fundamentally different internal structure from that of the Sun, where convection is limited to the outer third of the radius and the core is radiative. This full convection has important consequences. It means that these stars can access all of their hydrogen fuel over time, rather than only the fraction that sits in the core, and as a result, they have extraordinarily long lifetimes, potentially trillions of years, far exceeding the current age of the universe. No red dwarf that has ever formed has yet had time to exhaust its fuel and evolve off the main sequence, which means that our understanding of what happens to these stars at the end of their lives is entirely theoretical, with no observational examples to test the predictions. But the truly smallest stellar remnants are not red dwarfs. They are neutron stars, and here the word extreme takes on a qualitatively different character. A neutron star is the collapsed core left behind when a massive star, typically one that began its life with between 8 and roughly 25 solar masses, exhausts its nuclear fuel and undergoes a core collapse supernova. The core, initially composed of iron and other heavy elements fused during the final stages of the star's life, collapses under its own gravity to the point where protons and electrons are forced together to form neutrons, and the resulting object is supported against further collapse by neutron degeneracy pressure and the strong nuclear force. The typical neutron star has a mass of roughly 1.4 solar masses, close to the Chandrasekhar limit that defines the maximum mass supportable by electron degeneracy pressure in a white dwarf, and a radius of only about 10 to 12 kilometers. This means that a mass comparable to that of the Sun is compressed into a sphere roughly the size of a terrestrial city, and the resulting density is staggering. A teaspoon of neutron star material would weigh roughly 1 billion tons, or about the same as a mountain on Earth. The surface gravity of a neutron star is on the order of 200 billion times the surface gravity of Earth, and the escape velocity is a significant fraction of the speed of light, typically around 1/3 c. These numbers are not merely large, they place neutron stars in a physical regime where general relativity becomes essential for describing their structure, where the equation of state of matter at supranuclear densities remains uncertain and is one of the outstanding problems in nuclear physics, and where phenomena occur that have no analogue anywhere else in the observable universe. The most extreme neutron stars, in terms of the phenomena they produce, are the magnetars, a subclass first proposed theoretically by Robert Duncan and Christopher Thompson in the early 1990s, and subsequently confirmed observationally through the detection of soft gamma repeaters and anomalous X-ray pulsars. A magnetar is a neutron star with a magnetic field strength in the range of 10 to the 14th to 10 to the 15th Gauss, which is roughly 1,000 times stronger than the magnetic field of a typical radio pulsar and roughly a quadrillion times stronger than the Earth's magnetic field. To put this in perspective, the strongest sustained magnetic fields produced in terrestrial laboratories are on the order of 45 Tesla, or about 450,000 Gauss, which means that a magnetar's field exceeds the best human-made magnetic fields by a factor of roughly 1 billion. At these field strengths, the physics of the vacuum itself is altered. Quantum electrodynamics predicts that in fields above the so-called Schwinger critical field, approximately 4.4 times 10 to the 13th Gauss, the vacuum becomes birefringent, meaning that it splits polarized light into two components that travel at slightly different speeds, analogous to what happens when light passes through certain crystals. Observations with the Very Large Telescope in 2017 provided tentative evidence for this vacuum birefringence around the neutron star RX J1856.5 3754, though the result remains at the boundary of statistical significance and has not yet been independently confirmed. A magnetar's field is also strong enough to distort the shapes of atoms, stretching them into elongated cylinders aligned with the field lines, and to make the stellar surface opaque at energies where it would otherwise be transparent, producing spectral features that have been challenging to model. The energy source that powers a magnetar's emission is not rotation, as it is for ordinary radio pulsars, but rather the decay of the ultra-strong magnetic field itself. As the field evolves, it stresses the solid crust of the neutron star, and when the accumulated stress exceeds the breaking strain of the crustal material, the crust fractures in an event analogous to a starquake. These fractures can release enormous amounts of energy in very short bursts, and the most extreme such event ever recorded was the giant flare from the magnetar SGR 1806-20 on December 27, 2004, which released more energy in a fraction of a second than the Sun emits in roughly 250,000 years. The initial spike of the flare lasted about 0.2 of a second and had a peak luminosity that briefly made it the brightest extrasolar event ever detected from within the Milky Way at gamma-ray wavelengths. The pulse was so intense that it measurably ionized the upper atmosphere of the Earth despite originating at a distance of roughly 50,000 light-years, and it saturated the detectors on every gamma-ray satellite that was operational at the time. The oscillations observed in the decaying tail of the flare have been interpreted as seismic vibrations of the neutron star crust, providing one of the few direct probes of the mechanical properties of matter at nuclear densities, and analysis of these quasi-periodic oscillations has yielded constraints on the shear modulus of the crust, and by extension, on the composition and structure of the neutron star interior. The question of what happens at densities above those found in ordinary neutron star matter is one of the most active frontiers in astrophysics and nuclear physics. At the center of a massive neutron star, the density may exceed several times the nuclear saturation density, which is the density of matter inside an atomic nucleus, roughly 2.8 times 10 to the 14th grams per cubic centimeter. Under these conditions, the nature of matter is genuinely uncertain. One possibility is that the neutrons remain the dominant constituent, but interact through complex many-body forces that make the material stiffer than lower-density neutron matter. Another possibility is that at sufficiently high densities, the neutrons themselves dissolve into their constituent quarks, forming a phase of deconfined quark matter, possibly in a specific state known as color-flavor-locked color superconducting matter, in which quarks form Cooper pairs, analogous to the electron pairs in a conventional superconductor. A third possibility, which has been discussed intermittently since the 1980s, is the formation of strange quark matter, in which roughly equal numbers of up, down, and strange quarks are present, and which might, under certain assumptions about the strong force, be the true ground state of matter, meaning that it would be more stable than ordinary nuclear matter. If this so-called strange matter hypothesis, originally proposed by Edward Witten in 1984, is correct, then a neutron star that accumulates enough mass could undergo a phase transition to become a strange star, composed entirely of strange quark matter from its center to its surface, with dramatically different properties from a conventional neutron star. The observational signatures that would distinguish a strange star from a neutron star are subtle and have not been definitively identified, but the detection of gravitational waves from the neutron star merger event, GW170817, in 2017, placed important constraints on the equation of state of dense matter, favoring equations of state that are relatively soft, but not so soft as to conflict with the existence of two solar mass neutron stars, which have been observed. The most massive neutron star reliably measured as of the early 2020s is PSR J0740 Pulsar 6620, a millisecond pulsar in a binary system whose mass has been determined through the Shapiro delay, a general relativistic effect in which the pulsar's radio signals are slightly delayed when they pass through the curved spacetime near the companion star. The measured mass is approximately 2.08 solar masses, with an uncertainty of about 0.07 solar masses, making it one of the heaviest neutron stars known and placing important lower bounds on the maximum mass that the neutron star equation of state must support. Theoretical models that predict a maximum neutron star mass below this value can be ruled out, which eliminates a significant fraction of the proposed equations of state and constrains the behavior of the strong nuclear force at densities that cannot be accessed in terrestrial particle accelerators. The NICER instrument aboard the International Space Station has also measured the radius of this star by modeling the distribution of X-ray emission from hotspots on its surface as the star rotates, yielding a radius estimate of roughly 12 to 13 kilometers, which is consistent with equations of state that predict neutron stars are somewhat larger and stiffer than the minimum allowed by general relativity. The combination of mass and radius measurements for multiple neutron stars is gradually narrowing the space of viable equations of state and future observations. Particularly additional gravitational wave detections from neutron star mergers by the LIGO-Virgo-Cagra network are expected to tighten these constraints further. Turning from the smallest stars to the most massive, the upper end of the stellar mass spectrum presents its own set of extremes and puzzles. The most massive stars currently known have estimated masses in the range of 100 to perhaps 250 solar masses, though the uncertainties on these estimates are considerable and the subject of ongoing revision. The star R136A1, located in the R136 star cluster at the center of the Tarantula Nebula in the Large Magellanic Cloud, was initially reported in 2010 to have a mass of roughly 265 solar masses, based on spectroscopic analysis by a team led by Paul Crowther at the University of Sheffield. Subsequent reanalysis, published in 2022, revised this estimate downward to approximately 170 to 230 solar masses, depending on the stellar atmosphere models and binary status assumptions used. Even at the lower end of this range, R136A1 is an extraordinary object, far exceeding the mass of any star that can be found in the solar neighborhood, and its luminosity is estimated at several million times that of the Sun, making it one of the most luminous individual stars known. The existence of stars with masses above roughly 150 solar masses was itself a matter of theoretical debate for decades. The classical argument, developed by Arthur Eddington in the 1920s and refined by subsequent generations of stellar structure theorists, is that radiation pressure inside a sufficiently massive star becomes so intense that it exceeds the gravitational force binding the outer layers, causing the star to become unstable and blow itself apart. This so-called Eddington limit is not a single fixed mass, but depends on the composition and opacity of the stellar material. And for stars of solar composition, theoretical models suggested that it would prevent the formation or survival of stars above roughly 120 to 150 solar masses. The discovery of stars in the R136 cluster and in other young massive clusters with apparent masses above this threshold forced a re-evaluation of the relevant physics, and several mechanisms have been proposed to explain how such massive stars can exist. One is that the Eddington limit is not a hard barrier, but a regime in which mass loss becomes very rapid, and that stars can briefly exceed the limit during episodes of intense accretion before settling back below it. Another is that the opacity of the stellar material at very high temperatures is lower than some models assumed, allowing the Eddington limit to be higher than previously calculated. A third possibility, which has gained traction with the development of sophisticated three-dimensional radiation hydrodynamic simulations, is that radiation does not escape uniformly from the stellar surface but is channeled through porous structures in the outer layers, a phenomenon sometimes called porosity-modulated mass loss, which reduces the effective radiation force on the bulk of the stellar envelope and allows the star to remain bound at higher luminosities. The formation mechanism of very massive stars is itself a subject of active research. For lower mass stars like the Sun, the standard picture involves the gravitational collapse of a dense core within a molecular cloud, followed by the accretion of additional material through a disk. For very massive stars, this picture runs into difficulties because the intense radiation from the protostar, which reaches main sequence luminosities while still accreting, should in principle halt the inflow of material and prevent the star from gaining further mass. Simulations have shown that accretion can continue despite the radiation pressure if the inflowing material is channeled through a disk and the radiation escapes preferentially along the polar directions, perpendicular to the disk. But the details of this process and the maximum mass that can be assembled through disk accretion remain uncertain. An alternative formation pathway, which may be relevant for the most massive stars in dense cluster environments, is stellar mergers, in which two or more already massive stars collide and merge to form a single more massive object. The high stellar densities found in the cores of young massive clusters like R136, where stars are packed within a volume less than a parsec across, make dynamical interactions and collisions plausible on timescales of a few 100,000 years, which is short compared to the main sequence lifetimes of the stars involved. If R136A1 formed through one or more mergers, its extreme mass may not reflect the maximum mass that can be produced by accretion alone, but rather the maximum mass achievable through a combination of accretion and dynamical processing in a dense stellar environment. The luminosity of these most massive stars is so great that their radiation drives powerful stellar winds, which strip mass from the star at rates that can exceed 10 to the -4 solar masses per year, or roughly the mass of Jupiter every 10 years. Over the few million-year lifetime of such a star, these winds can remove a substantial fraction of the star's initial mass, and the material ejected into the surrounding interstellar medium enriches it with heavy elements synthesized in the star's core and in the nuclear reactions occurring in the wind itself. The nitrogen-enriched nebulae observed around many Wolf-Rayet stars, which are the evolved, stripped-down descendants of very massive stars, are direct evidence of this process. The most luminous star currently known, in terms of bolometric luminosity, which accounts for radiation at all wavelengths rather than just visible light, is a matter of some debate, but strong candidates include R136A1 and the star BAT 9998, also in the Large Magellanic Cloud, with luminosities estimated in the range of 6 to 10 million solar luminosities. At these luminosities, the total energy output of the star in a single second exceeds the Sun's annual energy output by a factor of roughly 200, and the radiation field near the stellar surface is so intense that it exerts measurable pressure on any material in the vicinity, shaping the surrounding nebula and potentially triggering or suppressing star formation in neighboring regions of the cloud. The shortest-lived stars are naturally the most massive ones, because the rate at which a star burns its nuclear fuel scales much more steeply with mass than the amount of fuel available. A rough scaling relation, confirmed by detailed stellar evolution models, is that the main sequence lifetime of a star is proportional to its mass divided by its luminosity, and since luminosity scales approximately as mass to the power of 3.5 for massive stars, the lifetime scales as mass to the power of -2.5. For the Sun, this yields a main sequence lifetime of roughly 10 billion years. For a star of 100 solar masses, the corresponding lifetime is only about 2 to 3 million years, and for a star of 200 solar masses, it may be as short as 1 million years or even less. These timescales are short not only by astronomical standards, but also by geological standards. A star of 200 solar masses could form, live its entire life, and explode as a supernova in less time than it takes for a modest amount of tectonic plate motion on Earth. This brevity has important consequences for where such stars can be observed. Because they live and die so quickly, they are found only in or very near the regions where they formed, which are the densest, most actively star-forming regions of galaxies. They do not have time to drift far from their birthplaces, and their deaths, which are among the most energetic events in the universe, enrich the immediate surroundings with freshly synthesized heavy elements, creating a feedback loop in which the products of massive star evolution influence the conditions for subsequent generations of star formation. The deaths of the most massive stars are themselves among the most extreme phenomena in astrophysics. For stars with initial masses above roughly 8 solar masses, the end state is a core collapse supernova, in which the iron core of the star, having exhausted all possible sources of nuclear energy, collapses in a fraction of a second to form either a neutron star or a black hole, and the gravitational energy released by this collapse, roughly 3 × 10⁻46 joules, blows the outer layers of the star into space at velocities of tens of thousands of kilometers per second. But the details of this process depend sensitively on the mass, metallicity, rotation rate, and magnetic field of the progenitor star, and the outcomes span a wide range. Stars at the lower end of the mass range that produces core collapse supernovae, roughly 8 to 25 solar masses, typically produce neutron stars and type II supernovae with relatively modest kinetic energies. Stars at the upper end of this range, perhaps 25 to 40 solar masses, may instead collapse directly to black holes with little or no visible supernova explosion, a scenario that has been dubbed a failed supernova, and for which there is tentative observational evidence in the form of massive stars that appear to vanish from observations without producing a detected supernova, such as the case of the star N6946 BH1 in the galaxy NGC 6946, which faded from view between 2009 and 2015. For the most massive stars, those above roughly 40 to 60 solar masses at solar metallicity, the situation is complicated by extreme mass loss during their lives, which can strip the star down to a bare helium core or even a carbon-oxygen core by the time of core collapse. These stripped stars are the Wolf-Rayet stars mentioned earlier, and their supernovae, classified as type Ib or type Ike, depending on whether helium lines are present in the spectrum, are systematically more energetic and produce faster ejecta than typical type II supernovae. A particularly extreme subclass, the broad-lined type Ike supernovae, sometimes called hypernovae, have kinetic energies 10 or more times greater than a standard core collapse supernova and are associated with the formation of rapidly rotating black holes. Some of these hypernovae are accompanied by long-duration gamma-ray bursts, which are the most energetic electromagnetic events in the universe, with isotropic equivalent energy releases of up to 10 to the 47th joules. Though the actual energy output is much lower because the emission is concentrated into two narrow jets along the rotation axis of the collapsing star, the connection between gamma-ray bursts and the deaths of massive stars was established observationally in the late 1990s and early 2000s through the detection of supernova signatures in the afterglows of several gamma-ray bursts, most notably GRB 030329SN 2003DH, and the physical mechanism is believed to involve the formation of a rapidly accreting black hole surrounded by a dense torus of material, with the jets powered either by the extraction of rotational energy from the black hole through the Blandford-Zinajek mechanism or by neutrino-antineutrino annihilation above the accretion disk. An even more exotic fate awaits the most massive stars of the very early universe, those formed from pristine gas with essentially zero heavy element content, the so-called population 3 stars. Theoretical models of star formation in the early universe, constrained by the conditions prevailing in the first dark matter mini-halos that formed a few 100 million years after the Big Bang, suggest that the first stars may have been substantially more massive than typical stars forming today, with masses potentially ranging from tens to hundreds of solar masses and possibly even higher, though the upper end of this range is uncertain and depends on the details of the fragmentation of the primordial gas clouds and the feedback effects of the protostellar radiation. For population 3 stars in the mass range of roughly 140 to 260 solar masses, theoretical models predict a unique type of explosion known as a pair instability supernova, in which the core of the star becomes so hot, exceeding roughly 1 billion Kelvin, that the photons in the core begin to convert spontaneously into electron-positron pairs. This pair production removes radiation pressure support from the core, causing it to contract, which heats it further and accelerates nuclear burning, triggering a thermonuclear explosion so violent that it completely disrupts the star, leaving no compact remnant at all, neither a neutron star nor a black hole. The entire mass of the star is expelled into the surrounding medium, and the nucleosynthetic products, which include large quantities of nickel-56 and other iron group elements, are predicted to produce a supernova with a peak luminosity comparable to the brightest events ever observed and a light curve that remains luminous for months to years. No definitive pair instability supernova has been observed, though several candidates have been proposed, including the extremely luminous supernova SN 2007 Bi which displayed some of the spectral and photometric characteristics predicted by pair instability models, but whose interpretation remains debated. Above roughly 260 solar masses, theoretical models predict that the pair instability collapse leads directly to the formation of a black hole without a significant explosion, because the nuclear energy released by the thermonuclear burning is insufficient to unbind the star and the entire object collapses. The most massive stellar black holes detected through gravitational wave observations have pushed the boundaries of this theoretical framework. The event GW190521, detected by the LIGO and Virgo observatories in May 2019 and reported in September 2020, involved the merger of two black holes with component masses of approximately 85 and 66 solar masses, producing a final black hole of roughly 142 solar masses. The more massive component, at 85 solar masses, falls squarely within the so-called pair instability mass gap, the range of masses between roughly 60 and 120 solar masses, in which stellar evolution models predict that pair instability supernovae should prevent the formation of black holes. The existence of a black hole in this mass gap challenges either the stellar evolution models, perhaps indicating that the pair instability process is less efficient than calculated, or the formation pathway of the black hole, perhaps indicating that it was itself the product of a previous merger rather than the direct collapse of a single star. The latter scenario is plausible in the dense environments of globular clusters or nuclear star clusters, where repeated mergers of smaller black holes could build up masses within the gap, and several groups have modeled this hierarchical merger scenario in detail, finding that it can reproduce the observed properties of GW190521 under reasonable assumptions about the cluster dynamics. Turning to the fastest rotating stars, the physics of rapid rotation introduces a range of phenomena that are absent or negligible in slowly rotating stars like the Sun. The Sun rotates with a period of roughly 25 days at its equator, which corresponds to an equatorial velocity of about 2 kilometers per second, a small fraction of its roughly 600 kilometer per second breakup velocity, which is the velocity at which centrifugal force at the equator would equal gravitational force and material would begin to be flung off the surface. Many stars, particularly massive stars on the upper main sequence, rotate much faster than the Sun, with equatorial velocities of 200 to 400 kilometers per second, being common among O and B-type stars, and some stars approaching or reaching their breakup velocities. The star VFTS 102, a massive O-type star in the Tarantula Nebula, has a projected rotational velocity, V sin I, of roughly 610 kilometers per second, making it one of the fastest rotating massive stars known, and its equatorial velocity, after correcting for the unknown inclination angle, is estimated to be close to its critical breakup velocity. At such extreme rotation rates, the star is significantly oblate, with its equatorial radius substantially larger than its polar radius, and the effective surface gravity varies dramatically from pole to equator, being lowest at the equator where centrifugal force partially counteracts gravity. This variation in surface gravity produces a corresponding variation in surface temperature and luminosity, a phenomenon known as gravity darkening or the von Zeipel effect, in which the equatorial regions are cooler and dimmer than the polar regions. The resulting spectral line profiles are broadened and distorted in characteristic ways that allow the rotation rate to be inferred, even when the star is too distant to be spatially resolved. But the most extreme rotation rates in the stellar universe are found not among main sequence stars, but among neutron stars, specifically the millisecond pulsars. The fastest known pulsar, as of the early 2020s, is PSR J1748 2446 AD, located in the globular cluster Terzan 5, which rotates at 716 revolutions per second, corresponding to a period of just 1.396 milliseconds. This means that a neutron star roughly 20 kilometers in diameter is completing more than 700 full rotations every second, and the equatorial velocity is approximately 24% of the speed of light. The centripetal acceleration at the equator of this star is roughly 10 to the 11th g, or about 100 billion times the acceleration due to gravity at the surface of the Earth, and the equatorial surface is moving so fast that it is close to the point where material would be flung off into orbit. The existence of such rapidly rotating neutron stars is explained by the recycling scenario, in which an old, slowly rotating neutron star in a binary system is spun up by the accretion of material from a companion star. The accreted material carries angular momentum, and as it spirals onto the neutron star's surface through an accretion disk, it transfers this angular momentum to the star, gradually increasing its rotation rate over a period of millions to billions of years. The process is self-limiting because the accretion also heats the neutron star surface, producing X-ray emission, and at sufficiently high accretion rates, the gravitational wave emission from asymmetries in the star or the magnetic field coupling between the disk and the star can balance the spin-up torque and prevent the star from reaching its breakup velocity. The fact that the observed millisecond pulsars have rotation rates well below the theoretical maximum, which is estimated at roughly 1,000 to 1,500 revolutions per second, depending on the equation of state, suggests that one or more of these braking mechanisms is effective, though the details remain under investigation. The most magnetically extreme objects in the universe, the magnetars already mentioned, are worth examining further in the context of how their magnetic fields originate and evolve. The leading model for magnetar field generation is the convective dynamo hypothesis, which proposes that during the first 10 to 30 seconds after the neutron star forms in a core collapse supernova, the hot, differentially rotating, convectively unstable proto-neutron star acts as a dynamo, amplifying an initial seed magnetic field to the extreme values observed. The efficiency of this dynamo depends critically on the rotation rate of the proto-neutron star at birth. If the initial rotation period is short enough, roughly 1 to 3 milliseconds, the dynamo can amplify the field to magnetar strengths, whereas a more slowly rotating proto-neutron star produces an ordinary pulsar strength field. This model predicts a correlation between the initial rotation rate and the magnetic field strength of the resulting neutron star, and it provides a natural explanation for why magnetars are rare, since only a small fraction of core collapse supernovae are expected to produce proto-neutron stars with the requisite short initial periods. An alternative or complementary mechanism involves the development of magnetohydrodynamic instabilities in the proto-neutron star, such as the Taylor-Spruitt dynamo or the magnetorotational instability, which can amplify the field on shorter timescales and to higher strengths than simple convective dynamo action. Distinguishing between these mechanisms observationally is challenging, but the properties of the magnetar population, including the distribution of magnetic field strengths, spin periods, and ages, provide statistical constraints that are gradually narrowing the space of viable models. The question of how the magnetic field of a magnetar decays over time is directly connected to some of the most extreme phenomena these objects produce. The field energy stored in a magnetar with a surface dipole field of 10 to the 15 Gauss is roughly 10 to the 47 ergs, which is comparable to the kinetic energy of a supernova explosion. This energy is dissipated over the magnetar's active lifetime, which is estimated at roughly 10,000 years, based on the observed population statistics, primarily through ohmic dissipation in the crust and through the unwinding of internal magnetic field structures that stress and crack the crust. The rate of energy dissipation determines the X-ray luminosity of the magnetar in quiescence, which is typically in the range of 10 to the 34 to 10 to the 36 ergs per second, well above what can be explained by the rotational energy loss of the star. The distinction between rotation-powered pulsars, whose emission is powered by the loss of rotational kinetic energy, and magnetars, whose emission is powered by magnetic field decay, is one of the fundamental taxonomic divisions in neutron star astrophysics, though there is growing evidence that the boundary between the two classes is not sharp. Several neutron stars have been identified that display properties of both classes, such as the high magnetic field radio pulsar PSR J184600258, which is normally a rotation-powered X-ray pulsar, but underwent a magnetar-like outburst in 2006, producing soft gamma-ray bursts and a sudden increase in X-ray luminosity. These transitional objects suggest that the magnetar phenomenon may be more of a continuum than a discrete category, and that the magnetic field strength required to produce magnetar-like behavior may be lower than the canonical 10 to the 14 Gauss threshold if the internal field geometry is sufficiently complex. Among the most extreme stellar phenomena in terms of energy output per unit time are the superluminous supernovae, a class of stellar explosions discovered in the mid-2000s that are 10 to 100 times more luminous at peak than ordinary core collapse supernovae, with peak luminosities exceeding 10 to the 44 eargs per second. The power source of these events is debated, and several mechanisms have been proposed. For the hydrogen-poor subclass, known as Type 1 superluminous supernovae, the leading model involves the spin-down of a rapidly rotating, highly magnetized neutron star, a magnetar, born in the core collapse. The rotational energy of a neutron star spinning at a period of 1 to 2 milliseconds is roughly 10 to the 52 ergs, which is more than sufficient to power the observed light curves if it is deposited into the expanding supernova ejector on a timescale of days to weeks, and the spin-down luminosity of a magnetar with a dipole field of 10 to the 14 Gauss and an initial period of 1 millisecond is a good match to the observed peak luminosities. This so-called magnetar spin-down model has been remarkably successful in fitting the light curves of many Type 1 superluminous supernovae, though alternative models involving the interaction of the ejector with a dense circumstellar medium which converts kinetic energy into radiation can also reproduce many of the observed properties. For the hydrogen-rich subclass, Type 2 superluminous supernovae, the interaction model is generally preferred because these events show clear spectroscopic signatures of the ejector running into hydrogen-rich material expelled by the progenitor star in the years or decades before the explosion. The most luminous supernova ever observed, as of the early 2020s, is generally considered to be SN 2016 APS, which was detected in January 2016 and reached a peak luminosity of roughly 5 times 10 to the 44 eargs per second, making it approximately 20 times brighter than a typical superluminous supernova and several hundred times brighter than an ordinary core collapse supernova. The total radiated energy of SN 2016 APS over its entire light curve was estimated at roughly 5 times 10 to the 51 ergs, which is comparable to the total kinetic energy of a standard supernova explosion and well above the typical radiated energy of 10 to the 49 ergs. The progenitor of SN 2016 APS is believed to have been an extremely massive star, possibly the result of a merger between two massive stars, with a total pre-explosion mass estimated at 50 to 100 solar masses, and the explosion mechanism may have involved a pulsational pair instability supernova, in which the pair instability process does not completely disrupt the star, but instead ejects several solar masses of material in a series of pulses, followed by a final core collapse supernova whose ejector collide with the previously ejected shells, converting kinetic energy into radiation with high efficiency. The coldest stars, in the sense of having the lowest effective surface temperatures, are the late type L, T, and Y dwarfs, which straddle the boundary between true stars and substellar objects. The coolest confirmed Y dwarfs detected by the Wide Field Infrared Survey Explorer, WISE, have estimated effective temperatures as low as roughly 250 to 350 Kelvin, which is comparable to the temperature of a warm day on Earth. These objects are not hydrogen-fusing stars. They are brown dwarfs, failed stars whose masses were too low to ignite sustained hydrogen fusion, and they are included here only to establish the lower temperature boundary of the stellar and substellar population. The coolest true star, meaning the coolest object that is sustained by hydrogen fusion, would be a red dwarf near the hydrogen-burning minimum mass, with an effective temperature of roughly 2000 to 2200 Kelvin. These temperatures are low enough that molecules including water, titanium oxide and vanadium oxide can form in the stellar photosphere, producing complex absorption spectra that are very different from the relatively clean spectra of hotter stars. The spectral classification of these objects is still being refined, and the boundary between the coolest M-type stars and the warmest L-type brown dwarfs is not sharply defined, because the observational properties transition gradually as the effective temperature decreases. At the opposite extreme, the hottest stellar surfaces known belong to certain white dwarfs and the central stars of planetary nebulae. which can have effective temperatures exceeding 200,000 Kelvin. These are exposed cores of stars that have shed their outer envelopes, either through the slow mass loss of an asymptotic giant branch star that produces a planetary nebula, or through the more violent stripping in a binary system. The hottest such objects are the PG 1159 stars, a class of hydrogen-deficient pre-white dwarf stars with effective temperatures in the range of 75,000 to 200,000 Kelvin and surface compositions dominated by helium, carbon, and oxygen, reflecting the nuclear-processed material from the star's interior. The hottest known PG 1159 star, RX J0439 86809, has an estimated effective temperature of roughly 250,000 Kelvin, though this figure is model-dependent and subject to significant systematic uncertainties. At these temperatures, the peak of the star's spectral energy distribution is in the extreme ultraviolet or soft X-ray range, and the star ionizes the surrounding gas out to large distances, creating an extensive zone of ionized hydrogen and helium. The effective temperature of a star is, of course, a measure of the energy flux per unit area of its photosphere, and it does not directly indicate the temperature at the star's center, which can exceed 1 billion Kelvin during the late stages of nuclear burning in massive stars and during the brief moments of a supernova explosion. The highest temperatures ever produced in stellar material occur during neutron star mergers and in the cores of core collapse supernovae, where temperatures briefly reach tens of billions of Kelvin, high enough for the thermal energy of individual particles to exceed the rest mass energies of pions and other hadrons, allowing the production of exotic particles that quickly decay and contribute to the neutrino flux from the event. The study of stellar variability has revealed its own set of extremes. Some stars exhibit periodic variations in brightness that are extraordinarily regular, serving as cosmic clocks of remarkable precision, while others vary chaotically or eruptively in ways that can change their appearance from one night to the next. Among the most regular variables are the millisecond pulsars already discussed, whose rotational stability rivals that of the best atomic clocks, with period derivatives, the rate of change of the period so small that they can be predicted years in advance with an accuracy of fractions of a microsecond. This stability has been exploited in the concept of a pulsar timing array, in which an ensemble of millisecond pulsars distributed across the sky is used as a galactic-scale gravitational wave detector, with the gravitational waves manifesting as correlated perturbations in the arrival times of the pulsar signals. In 2023, several pulsar timing array collaborations, including Nanograv, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, and the Chinese Pulsar Timing Array, announced evidence for a low-frequency gravitational wave background, consistent with the signal expected from a cosmic population of supermassive black hole binaries, marking a new use of stellar extreme precision for fundamental physics. Among the most erratically variable stars are the luminous blue variables, or LBVs, a rare class of massive evolved stars that undergo dramatic changes in luminosity and apparent temperature on timescales ranging from years to centuries. The most famous example is Eta Carinae, a binary system in the southern constellation Carina, whose primary component is one of the most luminous stars in the Milky Way, with an estimated luminosity of roughly 5 million solar luminosities. In the 1840s, Eta Carinae underwent an event known as the Great Eruption, during which it briefly became the second brightest star in the sky, with an apparent magnitude of roughly -1, before fading over the following decades. During this eruption, the star ejected roughly 10 to 40 solar masses of material, forming the spectacular bipolar homunculus nebula that surrounds the star today, and the total energy radiated during the event was comparable to that of a supernova, leading to its classification as a supernova imposter. The mechanism of the Great Eruption is not well understood, with proposed explanations ranging from a super Eddington wind driven by a deep-seated energy source, possibly related to the merger of two stars in what was originally a triple system, to a pulsational instability in the stellar envelope triggered by an opacity-driven mechanism. Light echoes from the Great Eruption, detected in reflected light from dust clouds at varying distances from the star, have allowed astronomers to reconstruct the spectrum of the eruption as it would have appeared to observers in the 1840s. revealing that the effective temperature during the peak of the eruption was surprisingly cool, around 5,000 Kelvin, which is inconsistent with a simple wind-driven model and favors an opaque, expanding photosphere more reminiscent of a stellar merger or an explosive event. The Eta Carinae system is also notable for its extreme binary interaction. The primary star and its less luminous companion, which is itself an extremely hot O or Wolf Rayet type star, orbit each other with a period of roughly 5.54 years in a highly eccentric orbit, eccentricity approximately 0.9. And at periastron the two stars approach to within roughly 1.5 astronomical units, close enough that the primary's dense stellar wind interacts violently with the companion's wind, producing a wind-wind collision zone that emits copious X-rays and accelerates particles to high energies. Observations with the Fermi Gamma-Ray Space Telescope have detected gamma-ray emission from Eta Carinae, making it one of a small number of colliding wind binary systems known to produce gamma rays, and the mechanism is believed to involve particle acceleration at the shock front between the two winds, similar in principle to the acceleration of cosmic rays at supernova remnant shocks, but occurring in a periodic, time-variable environment dictated by the binary orbit. The topic of extreme stellar composition deserves attention as well, because the chemical makeup of a star's surface carries information about the conditions under which the star formed and the nuclear processes that have occurred in its interior. The oldest stars in the Milky Way, those that formed in the first few 100 million years after the Big Bang, are expected to have extremely low abundances of elements heavier than hydrogen and helium, reflecting the near-pristine composition of the early universe. The most iron-poor star known, as of the early 2020s, is SMSS J8031 3667L839.3, discovered in 2014 by a team using the SkyMapper telescope in Australia. This star, which is a red giant in the halo of the Milky Way, has an iron abundance less than 10 to the negative 7 times the solar iron abundance, making it effectively iron-free at the level of detection. However, it has a relatively high abundance of carbon, roughly 10 to the minus 2.6 times the solar value, which classifies it as a carbon-enhanced metal-poor star. The extreme carbon enhancement relative to iron is believed to be the nucleosynthetic signature of a specific type of supernova, possibly a faint, mixing and fallback supernova in which most of the iron produced in the explosion falls back onto the compact remnant, while the lighter elements, including carbon, are ejected. If this interpretation is correct, then SMSS J0313-36670839.3 carries the chemical imprint of one of the very first supernovae in the universe, and its composition provides a direct window into the properties of the first generation of massive stars, none of which have survived to the present day. Other extremely metal-poor stars, such as He 1327-23R26 and He 01075240, have iron abundances in the range of 10 to the minus 5 to 10 to the minus 5.4 times solar, and they too show characteristic patterns of element ratios that have been used to infer the properties of the individual supernovae that enriched the gas from which they formed. At the opposite extreme, some stars have surfaces that are dramatically enriched in specific heavy elements, not because they formed from enriched gas, but because of physical processes that have altered the composition of their outer layers. The chemically peculiar AP and BP stars, for example, are main sequence A and B type stars with surfaces that show extreme overabundances of elements such as silicon, chromium, strontium, europium, and the rare earths, sometimes by factors of 1,000 or more relative to solar abundances. These enhancements are not a reflection of the star's overall composition, but rather the result of atomic diffusion, a process in which radiation pressure selectively lifts certain elements upward through the stellar atmosphere, while gravity pulls others downward, producing a stratified surface composition that can vary from element to element and from one region of the stellar surface to another. The strong, globally organized magnetic fields of these stars, typically in the range of hundreds to tens of thousands of Gauss, play a crucial role by suppressing convection and stabilizing the atmosphere against mixing, allowing the diffusion process to operate effectively over timescales of millions of years. The most extreme example of surface enrichment in an app star is the star Przybylski's star, also known as HD 101065, which was discovered by the Polish-Australian astronomer Antoni Przybylski in 1961 and whose spectrum defied classification for decades. Detailed spectroscopic analysis has revealed that Przybylski's star has an extreme overabundance of the rare Earth elements, including holmium, thulium, and lutetium, and that it appears to show spectral lines of short-lived radioactive elements such as promethium, technetium, and possibly even elements beyond uranium, including the transuranic elements such as plutonium and einsteinium. The identification of these lines is controversial because no known nucleosynthetic process can produce these elements in a stellar photosphere, and they have half-lives far too short to have survived from the star's formation. One proposed explanation is that the star is continuously producing these elements through a rare nuclear process, possibly involving the capture of high-energy particles by heavy nuclei in the stellar atmosphere. But this scenario requires physical conditions that are difficult to achieve, and the whole topic remains one of the most puzzling anomalies in stellar spectroscopy. The densest stars, in terms of average density, are again the neutron stars, with average densities in the range of 4 × 10 to the 14th grams per cubic centimeter, which is roughly twice the density of an atomic nucleus. But it is worth noting that the density within a neutron star is not uniform. It increases dramatically from the surface, where the density is comparable to that of iron at roughly 7 grams per cubic centimeter, through a series of increasingly exotic phases as one moves inward. The outer crust, extending to a depth of a few hundred meters, is a lattice of neutron-rich nuclei immersed in a sea of relativistic electrons, similar in structure to a terrestrial metal but composed of nuclei far more neutron-rich than any found in nature on Earth. Below a density of roughly 4 × 10 to the 11 grams per cubic centimeter, the neutron drip line is reached, and free neutrons begin to leak out of the nuclei and form a superfluid that permeates the lattice, creating a unique two-component system in which a crystalline solid coexists with a quantum superfluid. Deeper still, at densities above roughly 2 × 10 to the 14 grams per cubic centimeter, the nuclei dissolve and the matter transitions to a uniform liquid of neutrons, protons, and electrons, with the protons potentially forming a superconductor. The innermost core, at densities above 3 to 5 times nuclear saturation density, is the region where the greatest uncertainty exists and where the exotic phases mentioned earlier, including deconfined quark matter, hyperonic matter, in which strange baryons called hyperons appear, or Bose-Einstein condensates of pions or kaons, may be realized. The observational constraints on the properties of this innermost core come primarily from mass and radius measurements of neutron stars and from gravitational wave observations of neutron star mergers, both of which provide information about the pressure-density relationship, the equation of state, of the matter at these extreme densities. Another category of stellar extremes involves the environments in which stars are found. The most isolated stars in the galaxy are the hypervelocity stars. Objects that are traveling so fast, typically at velocities of 500 to 1,000 kilometers per second or more, that they are unbound from the Milky Way's gravitational field and are on trajectories that will carry them out of the galaxy entirely. The first hypervelocity star was discovered in 2005 by Warren Brown and colleagues, and it is believed to have been ejected from the vicinity of the supermassive black hole at the center of the Milky Way by the Hills mechanism, in which a binary star system passes close to the black hole. One star is captured into a close orbit, and the other is flung outward at high velocity. Subsequent discoveries have identified several dozen hypervelocity star candidates, though the interpretation of each one requires careful measurement of the star's distance, proper motion, and radial velocity, and some candidates have been reclassified as bound stars on unusual orbits. The Gaia Space Observatory has been instrumental in refining the census of hypervelocity stars by providing precise astrometric measurements for over 1 billion stars, allowing the full three-dimensional velocities of candidate objects to be determined with unprecedented accuracy. At the opposite extreme of stellar environments, some stars exist in extraordinarily dense stellar clusters, where the separation between neighboring stars is a tiny fraction of what it is in the solar neighborhood. In the core of a globular cluster, the stellar density can reach 10,000 to 1,000,000 times the density of the solar neighborhood, with typical separations between stars of only a few hundred to a few thousand astronomical units, comparable to the separations found in the outer regions of the solar system. In these dense environments, gravitational interactions between stars are frequent and can lead to a variety of exotic outcomes, including the formation of binary systems, the exchange of binary companions, the tidal stripping of stellar envelopes, and direct stellar collisions and mergers. The population of blue straggler stars found in globular clusters, stars that appear to be younger and more massive than the cluster's main sequence turnoff would predict, is believed to result from stellar mergers and mass transfer events facilitated by the high stellar density, and these objects represent a clear example of how the extreme stellar environment produces stars with properties that would be impossible to explain in isolation. The concept of extremity in stellar astrophysics extends naturally to the boundary conditions that define what a star is. At the upper mass end, the most massive known stars, at 150 to 250 solar masses, approach the theoretical limit set by radiation pressure and mass loss, and their properties are highly sensitive to factors such as metallicity, rotation, and binary interaction that are difficult to constrain observationally. At the lower mass end, the hydrogen burning limit at roughly 0.075 solar masses defines the boundary between stars and brown dwarfs, a boundary that is itself sensitive to metallicity, because lower metallicity gas is more transparent and allows the protostellar core to radiate energy more efficiently, slightly raising the minimum mass required for hydrogen fusion. At the high-temperature end, the surfaces of the hottest known pre-white dwarfs approach 250,000 Kelvin, and at the low-temperature end, the coolest hydrogen-fusing stars have effective temperatures barely above those of the hottest brown dwarfs. At the high-density end, neutron stars reach densities several times that of nuclear matter, and at the low-density end, the most extended red supergiants have average densities far lower than that of air at sea level, with some estimates placing the mean density of stars like UY Scuti at less than 10 to the minus 8 grams per cubic centimeter, roughly a millionth the density of air. The full range of stellar properties thus spans many orders of magnitude in every physical parameter, a factor of roughly 10 to the 10 in radius from neutron stars to the largest supergiants, a factor of 10 to the 20 or more in density from the most diffuse supergiants to the cores of neutron stars, a factor of more than 1,000 in surface temperature from the coolest red dwarfs to the hottest pre-white dwarfs, and a factor of roughly 10 to the 10 in luminosity from the faintest red dwarfs to the most luminous supergiants and superluminous supernovae. The discovery and characterization of these extreme stars has been closely tied to the development of new observational technologies and techniques, and the history of this development itself illustrates how the expansion of the observable parameter space repeatedly revealed objects that challenged existing theoretical models. The discovery of neutron stars as radio pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish was initially so unexpected that the possibility of an artificial extraterrestrial origin for the regularly pulsating radio signals was briefly considered, though the rapid identification of a natural explanation, a rotating neutron star emitting beamed radio emission from its magnetic poles, quickly followed. The subsequent discovery of the Crab pulsar in 1968, located within the remnant of the supernova of 1054 AD, confirmed the theoretical prediction, first made by Walter Baade and Fritz Zwicky in 1934, that neutron stars could form in supernova explosions, a prediction that had been regarded as speculative for over 3 decades due to the absence of observational evidence. The discovery of the first binary pulsar, PSR B1913+16, by Russell Hulse and Joseph Taylor in 1974, led to the first indirect detection of gravitational wave emission as the orbital period of the binary was observed to decrease at precisely the rate predicted by general relativity for a system losing energy through gravitational radiation, and this measurement provided the first empirical confirmation of the existence of gravitational waves 20 years before their direct detection by LIGO. The discovery of the first millisecond pulsar, PSR B 1937+21 in 1982 by Donald Backer and colleagues, with a period of 1.56 milliseconds, demonstrated that neutron stars could be spun up to rotation rates far exceeding those of the youngest, most energetic pulsars, and led to the development of the recycling model for millisecond pulsar formation. In the domain of optical and infrared astronomy, the development of adaptive optics systems and near-infrared detectors in the 1990s and 2000s allowed the individual stars in the dense cores of massive star clusters and in the galactic center to be resolved for the first time, revealing populations of stars whose properties could not have been measured with earlier technology. The spectroscopic characterization of the most massive stars in the R136 cluster, which required the resolving power of the Hubble Space Telescope and the ground-based VLT, demonstrated the existence of stars with masses well above the previously accepted upper limit, while the monitoring of stellar orbits around the Milky Way's central supermassive black hole, Sagittarius A, by the groups of Andrea Ghez and Reinhard Genzel provided not only the most precise mass measurement of a black hole, roughly 4 million solar masses, but also detected stars on orbits with periods as short as 16 years and closest approaches of only a few hundred astronomical units, placing them in the most extreme gravitational environment in which individual stars have been tracked. The star S2, also known as S02, whose orbit around Sagittarius A has been monitored continuously since the mid-1990s, passes through a region where the gravitational redshift and the special relativistic transverse Doppler effect are both measurable, and observations of its closest approach in 2018 by both groups confirmed the predictions of general relativity and ruled out several alternative theories of gravity at the level of a few percent. The gravitational wave era, inaugurated by the first direct detection of gravitational waves from a binary black hole merger, GDAR 150914, in September 2015, has added an entirely new dimension to the study of extreme stellar remnants. The component masses in GW 150914, approximately 36 and 29 solar masses, were higher than the masses of any stellar black holes that had been previously measured through X-ray binary observations, which had clustered in the range of 5 to 15 solar masses. This immediately raised questions about the formation channels for such massive black holes, with the leading possibilities being the collapse of massive low metallicity stars that retain their envelopes and avoid the pair instability gap, dynamical formation in dense stellar clusters through successive mergers, and formation in isolated binary systems through common envelope evolution. Subsequent gravitational wave detections, now numbering roughly 90 confident events as of the end of the third LIGO-Virgo-Cagra observing run, have populated the mass spectrum of merging compact objects and revealed several additional surprises, including the possible existence of compact objects in the so-called lower mass gap between roughly 2 and 5 solar masses, where the boundary between the heaviest neutron stars and the lightest black holes is expected to fall. The event GW 190814, for example, involved the merger of a roughly 23 solar mass black hole with a compact object of approximately 2.6 solar masses, which could be either the heaviest neutron star or the lightest black hole ever observed, and whose nature remains uncertain because no electromagnetic counterpart was detected. The interplay between observation and theory in the study of extreme stars is not a simple one-directional process in which observations confirm or refute theoretical predictions. In many cases, the observations have preceded the theory, revealing phenomena that were not anticipated and that required new physics or new astrophysical models to explain. The discovery of gamma-ray bursts by the Vela satellites in the late 1960s, originally designed to monitor compliance with the Nuclear Test Ban Treaty, is a classic example. The signals were detected, their cosmic origin was established, but the physical mechanism responsible for producing such intense, short-lived bursts of gamma radiation remained mysterious for nearly 3 decades, until the association with supernovae and the development of the collapsar and merger models in the 1990s and 2000s provided a coherent theoretical framework. Similarly, the discovery of fast radio bursts, first reported in 2007 by Duncan Lorimer and colleagues from archival data taken with the Parkes radio telescope, opened a new class of extreme transient phenomena whose physical origin is still debated, though the detection of a fast radio burst from the galactic magnetar SGR 1935+2154 in 2020 established a clear connection between at least some fast radio bursts and magnetar activity, lending support to models in which the burst emission is powered by the sudden release of magnetic energy from a magnetar's surface or magnetosphere. The extreme properties of stars are not merely curiosities. They serve as laboratories for fundamental physics under conditions that cannot be reproduced on Earth. The interiors of neutron stars probe the equation of state of cold, dense matter at densities inaccessible to terrestrial experiments. The surfaces of magnetars probe quantum electrodynamics in the strong field regime. The mergers of neutron stars and black holes probe general relativity in the strong field, highly dynamical regime. The nucleosynthesis in the first stars and in the most energetic supernovae probes, nuclear reaction rates and particle physics at high temperatures and densities. The evolution and mass loss of the most massive stars probe the physics of radiation hydrodynamics and the interaction between radiation and matter in regimes where the radiation field carries more energy and momentum than the material it pervades. Looking toward the future, several upcoming observational facilities are expected to extend the census of extreme stars significantly. The Vera C. Rubin Observatory, with its wide-field survey capability, will monitor billions of stars for variability and transient events, potentially detecting rare types of stellar explosions and eruptive variables that are currently undersampled. The James Webb Space Telescope, already operational, is providing unprecedented infrared sensitivity that is being used to study the faintest, lowest mass stars and brown dwarfs in the solar neighborhood, and to search for the spectroscopic signatures of the first generation of stars in the spectra of the most distant galaxies. The extremely large telescope and other ground-based 30-meter class telescopes under construction will provide the angular resolution needed to resolve individual stars in increasingly distant and crowded stellar environments, pushing the study of massive star populations to galaxies beyond the local group. And the next generation of gravitational wave detectors, including the Einstein Telescope and Cosmic Explorer on the ground and the space-based LISA mission, will extend the sensitivity to gravitational waves to lower frequencies and higher redshifts, potentially detecting the mergers of stellar remnants from the first generation of stars and providing direct information about the masses and spins of the first black holes and neutron stars. The accumulation of data from these and other facilities will inevitably reveal new extremes, stars with properties that lie outside the range currently known, and it is safe to predict that some of these discoveries will, like the discoveries of neutron stars, millisecond pulsars, magnetars, and hypervelocity stars before them, challenge existing theoretical models and require revisions to our understanding of stellar physics. The history of the study of extreme stars is, in a very real sense, the history of the expansion of the known physical universe. Each new extreme revealing a new regime of physical behavior, and each new discovery forcing a deeper understanding of the processes that govern the birth, life, and death of stars. One area in which continued observational progress is likely to produce significant results is the study of thermonuclear supernovae, the Type Ia events used as standardizable candles for measuring cosmological distances. While Type Ia supernovae are generally well understood as the thermonuclear disruption of carbon-oxygen white dwarfs that approach the Chandrasekhar mass of roughly 1.4 solar masses, either through accretion from a companion star or through merger with another white dwarf, there is a growing body of evidence that the population of Type Ia supernovae is more diverse than previously appreciated. Some events, classified as overluminous or super Chandrasekhar Type Ia supernovae, have peak luminosities and nickel-56 masses that exceed the maximum values predicted by the standard Chandrasekhar mass model, suggesting that they may originate from white dwarfs that exceed the Chandrasekhar mass, possibly supported against collapse by rapid rotation or strong magnetic fields. The most extreme such event, SN 2003FG, also known as the Champagne supernova, had an estimated nickel-56 mass of roughly 1.3 solar masses and a total ejecta mass that implied a progenitor well above the Chandrasekhar limit, possibly as high as 2 solar masses. This would require the white dwarf to be differentially rotating, with the centrifugal support allowing it to sustain a mass above the non-rotating Chandrasekhar limit, a configuration that is theoretically possible but whose stability and longevity are uncertain. At the opposite extreme, some type Ia supernovae are dramatically underluminous, producing only a few hundredths of a solar mass of nickel-56 and fading rapidly. And these events may be the result of partial thermonuclear detonations of sub-Chandrasekhar mass white dwarfs, triggered by the detonation of a thin helium shell on the surface rather than by the compression of the carbon-oxygen core to ignition conditions. The study of white dwarfs themselves has revealed extreme objects that push the boundaries of our understanding of degenerate matter. The most massive white dwarfs, with masses approaching or at the Chandrasekhar limit, are composed primarily of oxygen and neon, rather than carbon and oxygen, because they are the remnants of the most massive stars that avoid core collapse, those in the mass range of roughly 6 to 8 solar masses that ignite carbon burning in their cores but do not reach the conditions necessary for neon or silicon burning. The most massive white dwarf measured with high confidence, ZTF J1 plus 1458, has a mass of approximately 1.35 solar masses and a radius of only about 2,040 kilometers, smaller than the radius of the Moon, making it the smallest known white dwarf. Its extreme mass and compact size suggest that it may be the product of a white dwarf merger, in which two lower-mass white dwarfs spiraled together and coalesced to form a single, more massive white dwarf, rather than exploding as a type Ia supernova. The merger scenario is supported by the star's rapid rotation period of roughly 6.9 minutes, which is far shorter than typical for isolated white dwarfs and is consistent with the angular momentum expected to be retained from a merger event. The star also has an extremely strong magnetic field, estimated at roughly 600 to 900 megagauss, which is among the highest measured for any white dwarf and may have been amplified during the merger through a dynamo process analogous to the one proposed for magnetars. The oldest white dwarfs in the galaxy provide another kind of extreme. They are among the oldest surviving stellar objects, and their cooling ages, the time elapsed since they ceased nuclear burning and began radiating away their stored thermal energy, can be comparable to the age of the Milky Way's disk, roughly 8 to 10 billion years. The coolest and faintest white dwarfs, with effective temperatures below 4,000 Kelvin, are so dim that they are barely detectable even with the largest telescopes, and their colors are affected by the extreme pressure broadening of molecular hydrogen absorption in their dense helium-dominated atmospheres, producing an unusual upturn in their blue colors that was initially puzzling but is now understood as a consequence of the physics of collision-induced absorption. The measurement of the luminosity function of these old, cool white dwarfs, meaning the number of white dwarfs per unit volume as a function of luminosity, provides an independent method for estimating the age of the galactic disk, because the luminosity at which the white dwarf luminosity function drops sharply to zero corresponds to the cooling age of the oldest white dwarfs, which in turn corresponds to the age of the population from which they formed. The interrelationship between extreme stellar objects and the broader evolution of galaxies and the universe is an area of growing interest. The most massive and most luminous stars, though rare, have a disproportionate impact on their surroundings because of their intense radiation, powerful stellar winds, and explosive deaths. The concept of stellar feedback, which refers to the ways in which stars influence the gas from which future generations of stars will form, is central to modern models of galaxy formation and evolution. Massive stars ionize large volumes of the interstellar medium, creating Chi regions that can be hundreds of parsecs across and that are visible in the light of recombination lines, particularly the hydrogen alpha line at 656 nanometers. Their winds and supernova explosions inject kinetic energy into the surrounding gas, driving turbulence, creating hot, low-density bubbles that can merge to form galactic-scale outflows known as superwinds, and compressing neighboring gas clouds to trigger new episodes of star formation. The chemical elements synthesized in massive stars and dispersed by their supernovae enrich the interstellar medium with heavy elements, progressively increasing the metallicity of the gas from which subsequent generations of stars and planets form. Without the nucleosynthesis in massive stars, elements essential for the formation of rocky planets, and for chemistry as we know it, including carbon, oxygen, silicon, and iron, would not exist in the interstellar medium, and the universe would contain only hydrogen, helium, and trace amounts of lithium, the elements produced in the Big Bang. The connection between the first stars and the rionization of the universe is another example of how extreme stellar properties have consequences at the largest scales. The first stars, forming in dark matter mini-halos at redshifts of roughly 20 to 30, are believed to have been the primary agents responsible for ionizing the neutral hydrogen that filled the universe after recombination, transforming it from a neutral, opaque fog to the transparent, ionized intergalactic medium observed today. The efficiency with which these stars ionized their surroundings depended critically on their masses, luminosities, and lifetimes, all of which are extreme by the standards of the local stellar population. If the first stars were predominantly very massive, as some theoretical models suggest, they would have been very luminous and very hot, producing copious amounts of ionizing radiation, but living for only a few million years before exploding as supernovae. If they were more moderate in mass, they would have been less luminous individually, but longer lived, with a cumulative ionizing output that depended on the total number formed. The observational constraints on the epoch of rionization, from the cosmic microwave background, from the spectra of the highest redshift quasars, and from the Lyman alpha emission of distant galaxies, indicate that rionization was a gradual, spatially inhomogeneous process that was largely complete by a redshift of about 6, corresponding to roughly 1 billion years after the Big Bang. But the relative contributions of massive stars, smaller galaxies, and other sources such as accreting black holes to the total ionizing budget remain a subject of active investigation. Throughout this survey of extreme stars, a unifying theme emerges. The physical properties of stars are determined by a relatively small number of fundamental parameters, principally the initial mass, the chemical composition, and the angular momentum. But the consequences of varying these parameters across their full ranges are extraordinarily diverse. A factor of a few thousand in initial mass, from the lowest mass hydrogen-fusing stars to the most massive objects, produces a range of luminosities spanning more than 10 orders of magnitude, a range of lifetimes from a few million years to trillions of years, a range of surface temperatures from 2,000 to 200,000 Kelvin, and a set of possible end states, white dwarfs, neutron stars, and black holes that differ in their physical nature as profoundly as any objects in the known universe. The extreme objects at the edges of each distribution are not anomalies. They are the natural consequences of physical laws operating under conditions that differ quantitatively and sometimes qualitatively from the conditions that prevail in more typical stellar environments. Understanding these extremes requires not only the tools of observational astronomy, but also the machinery of nuclear physics, quantum mechanics, general relativity, magnetohydrodynamics, and statistical mechanics, and the fact that all of these fields converge in the study of stars is one of the reasons why stellar astrophysics, for all its apparent maturity, continues to yield discoveries that are genuinely surprising and that deepen our understanding of the physical universe in ways that extend far beyond the stars themselves. The study of extreme stars has also had a subtle but important cultural and institutional impact within astrophysics. Each new discovery of an extreme object, whether a pulsar, a magnetar, a hypervelocity star, or a superluminous supernova, has tended to catalyze the formation of new research communities, new conferences, and new journals or journal sections dedicated to the study of the new class of objects. The development of time-domain astronomy as a major subfield, with dedicated survey facilities and real-time alert systems that notify the global community within seconds of the detection of a new transient event, was driven in large part by the recognition that the most extreme and physically informative stellar events, supernovae, gamma-ray bursts, magnetar flares, fast radio bursts, and gravitational wave events, are inherently transient and require rapid follow-up observations at multiple wavelengths to be fully characterized. The infrastructure that has been built to enable this rapid response, from automated telescopes to worldwide communication networks to machine learning classification algorithms, represents a significant investment of resources and intellectual effort, and it has fundamentally changed the way stellar astrophysics is practiced. shifting the field from one that was primarily focused on static or slowly evolving objects to one that is increasingly oriented toward the detection and interpretation of brief, violent, and often unrepeatable events. In closing this account, it is worth recognizing that the concept of an extreme star is inherently relative and will inevitably shift as new observations expand the known parameter space. Stars that are considered extreme today may within a decade be surpassed by new discoveries that push the boundaries further, just as the discovery of each new fastest pulsar or most massive star has repeatedly revised the previous records. What remains constant is the underlying physics, the equations of stellar structure, the nuclear reaction networks, the equations of state, and the dynamical processes that together determine the range of possible stellar properties. The ongoing confrontation between these theoretical frameworks and the ever-expanding body of observational data is the engine that drives progress in the field, and the extreme stars, situated at the edges where the predictions are most uncertain and the observations most challenging, are the most powerful tests of our understanding. Each extreme star that is discovered and characterized, whether it conforms to theoretical expectations or violates them, adds to the cumulative knowledge that allows the full diversity of the stellar population to be understood not as a catalogue of disconnected curiosities, but as a coherent, interconnected manifestation of the physical laws that govern the universe.